And, and hello, everybody. My name is Gerard Guillamet, and I'm a postdoc researcher at the Barcelona Supercomputing Center. And in this presentation, what we are going to see is fluid structure simulation using wind energy using Alya HPC. The motivation of this presentation was to perform a simulation of a full wind turbine blade. And as you most probably know, these kind of structures are quite complex in terms of structures, in terms of the structure, because they have different materials, internal parts, and well, in terms of modeling, it's usually are difficult to work. For instance, when you have to generate the mesh, well, the use of 3D elements is usually quite complex, and also the number of degrees of freedoms increase. So usually in the literature, people usually prefer to use shell elements or beam elements. The thing is that, well, when you use these kind of elements, we lose part of the geometry details, and also in terms of the material point of view, we don't have the 3D full stress. Another motivation that was in this work was to use, well, to perform a large scale simulation of this wind turbine blade using a supercomputer, and also the use of finite parallel code. So the main objectives of this work is to first develop a reliable, elastic simulation of a full wind turbine blade, taking into account all the details of the structural parts and materials, and also to conduct a large-scale simulation in an exascale supercomputer. The contents of this presentation are basically divided in 4 main blocks. Okay, the first one is the description of the finite element code that we are using, that is Alya. Then the second block is related to the framework to solve the fluid structure interaction in an HPC environment. And also we are going to see some benchmark tests. And then the third block is the main case study that is going to be a wind turbine blade, as we are focused on the wind energy field. And finally, the conclusions and the future work. So as we have seen also in previous presentations, the Alya is the code that we are using at BSC in order to perform multiphysics and parallel finite element simulations. It has been run in other supercomputer facilities, and it has been scaled up to 100,000 cores. And well, it has hybrid parallelization by MPI, OpenMP, and CUDA, and also it has other features such as different kind of mesh partitioning methods, and also some variety of in-house solvers that are fully developed in parallel. Moving to the framework of the fluid structure in order to perform the fluid structure interaction, in this case, we have collaborated in the other teams from Alya, from computational fluid dynamics, because this simulation is a simulation of 2 physics, the physics of the solid mechanic problem and the physics of the fluid dynamics problem. For the solid mechanics, as we can see here, we have different kind of we have solved different kind of structures. For instance, this full wind turbine blade that in this case we did an analysis of buckling and post-buckling behavior of this structure, or also these other simulations of this solid shell structure, or for instance this full-scale fuselage with the detail of the stringers, and that was a simulation of more than 150 millions of degrees of freedom. Then moving to the computational fluid dynamics module of Alya, we have done several simulations in LES, and that we use the Bremen algorithm and low dissipation EMAC convective term. Here we can see a full aircraft with an LES simulation, or this two-blade rotor with a sliding mesh. So this would be the two ingredients, no? But also are very important the coupling algorithm that we use to solve this coupling simulation. That for this project we use a Gauss-Seidel algorithm that we can use also strong and weak couplings, and also we have different kind of relaxation schemes such as ICANN and IQN. In terms of solvers, we are also investigating a proper solver for the solid mechanic problems, because usually the solid mechanic problem, due to the complexity of the structure, and this can be very expensive in a coupling simulation. So we work also with collaboration with the MAMS consortium in order to find a proper solver to solve this kind of simulation. Now let's see some benchmark tests. This is on the top. We have a typical benchmark test. Is just in 2D, but and it's for just laminar flow. But it's a channel with an inflow, and then here we have a beam that is flexible. And then we compare the displacement and the velocity at one point of this flexible beam, how it behaves. So the results, as we can see here, we are compared with other numerical simulations in the literature. And well, this example was just to see if we are reproducing well the physics of the problem. On the other side, as in this project, we are in the field of wind energy. We decided to tune this example with the air properties, and to see if we were capable to solve this problem. In this case, we are using the LES wall turbulence model that makes no sense in 2D. But the objective of this example is just to see the robustness of the whole framework, in order to perform this fluid structure simulation. As you can see here, the beam deflects a lot, and also there are these vortices that makes different deformation of the beam. Now let's see the main case study of EoCoE, that is the simulation of the wind of a 30 meters wind turbine blade. We selected a benchmark case study from NREL that this blade is really interesting, because we have a lot of information about the materials and details of the structure. Is a 30-meter wind turbine blade, and well, it's for a wind turbine horizontal axis. So what we decided is to mesh all the wind turbine blade with full 3D elements. As you can see here, it's just the blade tip. As an example, because well, in this presentation we have started just for the blade tip, and as we can see here is we mesh this geometry with hexaedrons and prisms for the solid domains. This was quite challenging, because this structure, as we have seen, is quite complex. And from the fluid domain, we did the mesh with using linear for tetrahedrons. Okay, so this is the numerical setup. As I have said, we are going to show preliminary simulation of the wind turbine blade, just this tip of the blade. As we can see here, the blade tip is fixed at one side, okay, and then the other region is free to move. Is inside the channel of 5 meters per 8 meters width, and it has a velocity of 8 meters per second. Okay, so the setup of the fluid dynamics, we use the LES turbulence model with this velocity of air with 8 meters per second. In the structural dynamics problem, we use large deformations with geometrical nonlinearities. We use an implicit Newmark time integration scheme for the resolution of the problem. And for the material point of view, we use an orthotropic, San Bernard orthotropic material law. Okay. Then for the coupling algorithm, we use staggered explicit implicit algorithm. This is the well-known Gauss-Seidel. And well, this simulation was run in Mare Nostrum 4 with 288 CPUs for the fluid domain and 360 CPUs for the solid domain. Okay, so here we can see some results of this fluid structure interaction. As we can see here, we can see the different flow around the deformable body on the left side, and on the right side we have the overall computational cost for both solvers. Okay, here we are really interested to have an efficient fluid structure interaction simulation. So as you can see here, the times for the fluid and the Aleph-4 solver are less than 1 second, because this the solver that we use is explicit. But for the solid mechanics problem, we use an implicit time integration scheme, and the times are around, well, less than five seconds. This is something that we are trying to improve and to optimize, also with collaboration with MAMS consortium, in order to find a proper setup and a proper solver in order to equalize these times into the coupling simulation. Okay. So finally, the conclusions, we have presented an HPC fluid structure framework in order to solve high fidelity realistic simulations. This methodology and framework has been devised particularly for wind energy in order to run on exascale supercomputers. As a preliminary test and a preliminary setup, we decided to use just the blade tip in order to analyze if all the framework works well and if we are capable to solve this kind of problems and the difficulty that we have behind that. And also the use of, 3D stress elements for the structure that is demonstrated that can be a competent technology if we have computational resources and also if we have a proper mesh, in comparison to other approaches that are used in the literature. So the next steps from that is that to simulate the full wind turbine blade with the fluid structure interaction. We already did some tests with just the structural analysis of the full wind turbine blade that will be explained tomorrow from other people from the MAMS consortium. And other steps is other future work and next steps is to use subcycling steps on the fluid domain. This is a method in order that may save overall CPU times and I/O transfer and I/O communications. Also, the use of dynamic load balancing is another feature that can improve the node overload between both physics problems. And as I said, there is the part of the solver, in the solid domain that we use. Well, we collaborate with MAMS in order to find a proper solver to deal with this kind of simulations. Thank you very much, and I would be very glad to answer any doubt on that presentation. Thank you.
Thank you, Gerard. Is there any questions here?
Yes, can I ask a question, Julien?
Yes, please, Mathieu, go ahead.
Thank you. So, Mathieu Lobet from Maison de la Simulation. Thank you for your talk. I know that in the framework of EoCoE, you want to simulate a real farm of turbines on complex terrain. And I would like to know, in such a case, you would like to have dynamic blades or just static blades?
The idea, when one of my colleagues will explain in another presentation, that we are trying to simulate dynamic blades.
Okay, wow. Is it, I think it's challenging. Is it feasible with forthcoming exascale supercomputers, or you will need to go beyond this level of power?
Well, it's a very difficult question to answer. I don't know. I mean, it's something that we will see. I mean, for sure that, as you can see, this level of detail increase the problem size. So
Okay.
we will have to be able, and also it adds the difficulty if then we model the full wind turbine blade and this stuff, that can appear also other complications and some limitations maybe on the computational resources or whatever. So but this is something that we are trying to see or to understand.
Oh, sorry, this is Herbert. When could I contribute my opinion to this respect? So what I see first is perhaps one of the last slides from Gerard. For the moment, we see that the solids is taking much more than the fluid. Yeah, this is the first step. So if we had these kind of times, it would mean that if we want to do the full fluid structure, it would take 10 times more than if we only do the fluid. No, what we see here, approximately 0.5 seconds for the fluid and close to 5, perhaps not 10 times, 5 times more. So doing a real simulation of a wind farm with the wind turbines will be very expensive. And when we talk about the exascale, the important thing is, will we have a full exascale machine to do some test simulation? Perhaps we could run a real wind farm. In practice, the exascale computers means that we will have something that is 10 times bigger than what we have now. So in the short term, we could do perhaps a couple of wind turbines. And then this point of these times is something that we are starting to work with Gerard, and it depends a lot on the solver mainly. So depending on what we get on the solver, and we still have lots of work to do, and I hope that this can continue in EcoFree. Most probably, if we got a really good solver, obviously, no, most probably. If we had a good linear algebra solver, these blue times would fall significantly. The key CPU time in this solid simulation is a solver. So,
okay.
And well, we don't know for the moment if we will be able to solve this linear algebra problem quickly or not, but we will continue working, and we have lots of expertise within ECO. And if this were possible, then I believe it's feasible to do the full wind farm. Then you have to speak about how much time you can simulate this real full wind farm, but you can do it, hopefully.
Okay. Do we have time for a last question, or it's?
Yes, go ahead.
Yes, I was wondering as well, since it's quite impressive, how do you collaborate with manufacturers and electricity companies like Iberdrola? Are they strongly interested in your work, or for the moment it's not really used for real test case? I mean,
Yeah. Well, Gerard, do you prefer me to answer this
Yes,
question?
yes, of
Because
course.
it's like
Yeah.
Gerard works on the solids part, but he's not deeply involved in our interaction with Iberdrola and the
okay.
companies. So what I can say about this part, I would say is not of direct interest to Iberdrola. In our strongest collaboration within BSC is with Iberdrola, obviously, and Iberdrola is a wind energy producer, so they have lots of wind farms,
Mhm.
and this is not the target for this specific topic. So we have like two topics in EoCoE. We have the simulation of the wind farms, yeah, of the flow over complex terrain, and these are simulations that typically, well, we can simulate a week. When we simulate this, we can simulate some rotations of the wind turbine. These kind of simulations are more of interest to the people that produce the wind turbines. Yeah,
Okay.
they if they could have these real simulations, they could better optimize
The
fatigue
shape,
of
yes.
these wind turbine blades and this kind of stuff, the shape of the wind turbine. So, and I at the beginning of EoCoE, I got a support letter from Vestas. Vestas is the biggest wind turbine producer in the world. They are from Denmark, and well, I am hoping that at the end of EoCoE 2, I can show them this and a bit more advanced presentations, and that they are still interested. And this like would open up a second branch of collaboration with the industry. It's still wind energy, but it's like Vestas is not a competitor for Iberdrola. Vestas sells
Yeah, it's
wind
more.
turbines to Iberdrola.
Okay,
And
yes.
so we would like to open this second branch, but we still have lots of work to do.
Okay.
Thank you, Gerard. Thank you, Herbert.